Okay, I'm aware that the ideas underlying nuclear magnetic resonance and MRIs is reasonably complicated. So what I'm going to do is just give you a quick walkthrough of this animation that we're going to have a play with in class before we do, and hopefully that'll give you a clearer sense of what all of this means. Now, what we've got here is a grid of how many? Of 20 hydrogen atoms. We can change the hydrogen nuclei, sorry. We can change the type of nucleus that we're using here in this drop-down menu, but we'll leave it on hydrogen because that's what we've been talking about. And across this region, I have a strong electromagnet that I can vary from 0 to 3 Tesla. And then I also have a radio wave source below here where I can fire radio photons at these hydrogen nuclei. You'll see now they're kind of wobbling back and forth between their two allowed states. It's kind of random. They don't emit any energy when they change because the two energy states have the same energy because there's no magnetic field being applied at the moment. So what I'm going to do is just increase the magnetic field and we'll observe what happens to the hydrogen atoms. I'll increase it to 2. And you'll see that most of the hydrogen atoms have now arranged themselves so that they're in line with the magnetic field. Some of them are still sitting in the high energy state, but most of them have aligned themselves with the magnetic field. The precession is not quite clear from this animation, and that's why it says it's simplified, I think. All of these hydrogen atoms will actually be precessing about the vertical axis, but this animation does make it clear that there are 2 states that the hydrogen atoms can exist in, and these 2 states can be represented in an energy diagram here, where we have most of the atoms sitting in the low energy state most of the time, and a few will be sitting in the high energy state, but it's much less likely that an atom will exist up there. Now, what we can do is bombard this with photons, and I'm going to create a little trickle of radio photons coming up here. And we can see that we're now firing radio photons through, and nothing is really happening. And currently we're firing photons of 10 megahertz, and that's very low. It's too low to excite any of these hydrogen atoms up to the higher level. But what we can do is we can gradually increase the frequency, and as I do, in fact I'm going to increase the trickle a little bit more so we can see it a bit more clearly. As I increase it, if you have a look over here at the energy level diagram, you can see it shows us when we're getting to the right sort of energy level to match the difference in energy of the 2 allowed states for the hydrogen nuclei. So you can see that now I am causing excitation of the nuclei, and if we look here, we have many nuclei in the excited state, and they drop down and then they're re-excited by the photons that arrive, and each time they drop down from the excited state to the low energy state, we get a radio photon emitted, a radio photon of the same frequency emitted. I'm going to just reduce the intensity a little bit so that we don't have quite so many photons, and we can observe a little bit more clearly what's going on. So if we observe a photon, if a photon collides with a low energy nucleus, like we'll focus on this one and just wait for a photon to collide with it, here we go, and it bumps it up, and then eventually it drops back down and it fires that radio photon out again. And so this is the process of nuclear magnetic resonance, and this is about the level that we need to be able to explain it. That the hydrogen nuclei exist in 2 states, one which is stable and low energy, and one which is higher energy when we have a magnetic field applied. And as it drops down from the high to the low, it will re-emit a radio photon, and we can bump it up by hitting it with a radio photon of that same frequency. So for this 2 Tesla field, it looks like the frequency photon that corresponds to the energy difference is 85.2 megahertz. Alright, so now let's have a look at how this can be used in an MRI. So we'll click on this MRI tab up here. So here we have a chap whose head is full of hydrogen atoms, just like yours or mine is, and his head is inside this simulated MRI scanner, and we can make these hydrogen atoms emit radio photons. If let's just use the one that we had previously. So if we increase this to 2 Tesla, we can see that now the hydrogen atoms have mostly aligned themselves with the field. We have the odd one that's still in the high energy state. And what we're going to do is start to fire some radio photons at this guy. And we'll go up to, what was it, 85.6, I think. Okay, and then if we turn on our radio frequency coil, we've got it on wave view. We'll change it to photon view. We can see that now the photons that we send in are exciting the nuclei in the patient's head, and they're hitting the detector, and so we're getting a signal from all parts of this guy's head. Okay, so that's how we can use it to make the hydrogen nuclei in the patient emit radiation that we can then detect and locate. However, an additional thing that we need to be aware of is, so let's give this poor guy a tumor. So he's now got a tumor inside his head up here. And a tumor has a different density of hydrogen atoms to the surrounding tissue, which is represented here by a big clump of lots and lots of hydrogen atoms there. And in this 2 Tesla coil, 2 Tesla magnetic field, we know that we need 85.6 megahertz to excite the nuclei. And what we want to do now is make the field slightly stronger or weaker in only that area, so that we can slightly reduce or increase this frequency and stimulate only those. And this I've had to play around with, but it's kind of tricky to do in the simulation. And the way I'm going to do it is I'm going to completely reduce the main magnet's magnetic field. And I have these gradient magnets that can produce a non-uniform magnetic field. If I increase this one, I can make the fields stronger on the sides and weaker, so no difference in the middle. I'll increase the field on this side, and I'll be decreasing that uniform field on this side. So I'll show you what that looks like. If we turn this up to 2, you'll see that the field on the right, if I increase the horizontal gradient magnet, the field on the right will increase while the field on the left will decrease. And I can use the vertical gradient magnet to increase the field at the bottom and decrease the field at the top. So because I'm decreasing the field at the top and the tumor is near the top, what I'm going to try to do is create a lowered magnetic field there. So I've got a lower magnetic field there, which means I'm going to need a slightly lower frequency. So maybe we'll try 84 megahertz. This is trial and error. There is a mathematical rule for figuring this out, but we'll just work with trial and error. Oops, I'll put the tumor back. If only it were that easy. Now we can increase the power, and we can see where we're getting the emission from. You can see we're not really getting any emission from that region where the tumor is. I think we're going to need to go down a bit more. So how about 82? So now it seems like we're exciting the ones that are about at this level. So we haven't gone down far enough. About 78. now you can see that we're getting emission of photons from only this sort of region. Then we can do the same thing horizontally, and if we increase it horizontally, what happens? Yeah, so then what we can do is increase it horizontally and slightly increase this frequency to produce emissions from only this area. So the non-uniform magnetic field allows us to kind of localize the region that is emitting photons, and thereby we can produce an image of just that region. So I hope that clarifies some of the aspects of this nuclear magnetic resonance and magnetic resonance imaging.